Good morning, everyone. Let's get started. So we continue our discussion on broadcast channels in this class. In the last class, I sort of gave a definition of what a broadcast channel is. It's basically a channel where you have one transmitter and multiple receivers. The goal is to design coding schemes to communicate reliably across such broadcast channels. And our interest is in finding out what set of rates are achievable. So, at what rates can we communicate while simultaneously ensuring that the probability of error is vanishingly small, right? So, and as we did in the case of the multiple access channel, the achievable rate region or the capacity region is simply defined as the closure of the set of all rate pairs which are achievable, right? And towards the end of the class, we saw some simple bounds on the achievable rate region, on the capacity region. Uh, so we saw that if we do TDMA, then essentially the line joining these 2 points is achievable, where each of these are the individual capacities, where one user remains, where you communicate to only one of the receivers, whereas the other receiver gets absolutely nothing. Right? So if we define C1 as the maximum of overall possible Px of I of x comma y1, and C2 to be the maximum overall possible Px of the mutual information between x and y2. So these are essentially the capacities to user 1 to receiver 1 and capacity to receiver 2 respectively. And note that the maximizing input distribution need not be the same for these two different mutual informations. So clearly, if you want to communicate to only one of the users, then either C1 or C2 is achievable. So either R1 equal to C or close to C1 or R2 close to C2 is achievable. And by time sharing, essentially by using TDMA, any point on the line joining these two is also achievable, right? And we saw some simple outer bounds to see what is not achievable for the two user broadcast channel. Certainly, it's impossible to communicate at any rate above the individual capacities. So obviously, any point above this line and any point to the right of this line is not achievable. And then we also saw an outer bound on the sum rate, an upper bound on the sum rate. And then this is, as we did in the multiple access channel case, we saw that even if we combine the two receivers, even if, let's say, you have one super receiver who gets to see both y1 and y2 simultaneously, it is still impossible to communicate at any sum rate above C12, where C12 is the maximum uh, overall Px of the mutual information between x and y1, y2. Right? And that corresponds to this line with slope -1. So we know that any rate pair outside this red pentagonal region is not achievable, certainly not achievable. And we know that any point within this triangle is achievable. So the obvious question that we want to address is, what is achievable in between these two? What is the exact characterization of the achievable rate pairs? And it will turn out that for certain classes of broadcast channels, we know what the exact answer is. We'll give an exact capacity characterization as though it's some convex set which lies which contains this triangle but is certainly strictly within this pentagon. But for certain channels, it turns out that we don't know what the exact characterization is. Even to date, the best inner and outer bounds don't always match for general broadcast channels, and there is a gap. So we'll have one rate region which we know is certainly achievable. That's indicated by the curve below or the region below the blue curve, and we'll have an outer bound which says that any region outside the red curve or any region above the red curve is not achievable. And there's still a gap between these two. Okay, but to start to begin with, at least for we will look at channels where we know the exact capacity characterization. All right. And at the very end of the class, I also showed that the actually, if you want to, if your only interest is in finding out what the capacity region is, then the capacity region, if assuming you have only private messages, the capacity region depends only on the marginal probabilities. So it only depends on py1 given x and py2 given x, rather than the exact interdependence between y1 y2 in p y1 y2 given x. Right? So it suffices to, I mean, when we want to analyze the capacity region of a particular broadcast channel, it suffices to simply look at the class of channels which are where py1 y2 given x is py1 given x times py2 given x. Okay, and that is indeed what we will do in this particular course. So we'll only restrict ourselves to channels which can be expressed as a product distribution. Okay, so in particular, if you want to look at a specific example, then the following channel where you transmit a single bit x, the bit x is corrupted independently with probability p to get y1 and y2. So this channel has the same capacity region as the following channel over here, where X is passed through only one BSC, and that output is duplicated at both receivers Y1 and Y2. Okay, and so that's a very important observation that we will make use of. All right. So any questions regarding the discussion so far?
Uh, Sir, if
Yes.
I'm sorry, so if the number of channels or in the broadcast channel we have constituted two user, now if
Correct.
it is one user, will the graph look like some sphere or something like some solid structure having curved thing?
Yeah, so if it's a three user broadcast channel, then obviously you have three rates R1, R2, and R3, and then so it will be a three-dimensional shape, right?
Yes, yes.
Uh, so yeah, so in general, it's going to look like some weird convex shape, which is of course harder to visualize over here. So in general, for a three user broadcast channel, uh, the achievable rate region would look some region like this, right? So it may not be spherical, but it could be some three-dimensional region,
Yes, yes.
right? And of course, I mean, for more than three users, it's even harder to visualize it. Right? So typically, what some people look at, since it's not possible to characterize the exact rate region, sometimes people look at this just the sum rate. You'll try to find out that scheme which maximizes the sum rate, and that provides some measure of performance of a particular scheme, although it may not be the best thing to look at in all scenarios, because after all, you could always have you could have a scheme where the sum rate is large, but maybe only some users are getting a very high rate, whereas the other users are not getting anything at all. So there are many aspects. So when you have a multi-user communication scenario, there are many aspects to consider, where it's not just the throughput. Maybe some, so you can't obviously have so having a large sum rate would be good in terms of numbers, but then if maybe one user doesn't get to talk at all or gets to talk very little, then it's unfair to him. Or there may be some scenarios where even the person who has the worst channel and who cannot communicate at a very high rate still needs to communicate, because after all, if you want to talk on your cell phone, you should be given some you should be given a certain assured quality of service, and those aspects come into play in real world scenarios. So that is why we look at, so when we talk about the achievable rate region, it tells you everything that is achievable, right? Not just one particular sum rate. So you know that any point in that rate region is achievable, any point outside the rate region is not achievable. So it's up to the system designer to decide what is the right rate point to be operating at, so that all the other criteria are also satisfied. Okay.
Yes. Thank you.
So, any other questions? All right. As I mentioned previously, we still don't know what is the exact capacity region for general broadcast channels. So it turns out that we can make some statements, we can give a complete characterization for a certain class of broadcast channels where, let's say if you have two users, then one user gets sees a better channel than the other user. In particular, we look at the following class of degraded broadcast channels, where the channel to, let's say, user 1, so let's say the channel to user 2 is worse in some sense than the channel to user 1. Okay, and so this is a concept that we've seen in one of the early classes. So in particular, if you have a broadcast channel P, Y1, Y2 given X, then we say that the second receiver, or Y2, is physically degraded with respect to the first receiver, or Y1, if X, Y1 and Y2 form a Markov chain. So conditioned on Y1, Y2 is independent of X. So essentially, one way of thinking about this is that you have X, you pass it through a channel Py1 given X, right? And so the output Y1 is passed through another channel Py2 given Y1. So to get Y2, so user 1 gets to observe the output of the first channel, whereas user 2 gets to observe the output of the second channel. So that's one way of thinking about a physically degraded broadcast channel. So here it's evident that user 2's observation is obviously a more noisy observation than what user 1 sees. So that is why we say that user 2 is degraded with respect to user 1. User 2 is physically degraded with respect to user 1. Okay, so that's the notion of physical degradation in a broadcast channel. So another way of looking, another quick one example of this is when, let's say, you have X. Let's assume that these are Gaussian channels. So X is passed through an AWGN channel. Let's call this Z1 to get Y1, and user 1 sees the output of the first AWGN channel. So Y1 is passed through another AWGN channel to get Y2, Z2. Right, so let's assume that Z1 is Gaussian with zero mean and variance sigma square, and Z2 is Gaussian with zero mean and variance sigma 2 square. Okay, so in this case, Y2 is physically degraded with respect to Y1. So we say that Y2 is physically degraded with respect to Y1. Okay, so here it's obvious that Y2 is getting a worse copy than Y1. So obviously, if you wanted to communicate at a certain rate, generally the rate that Y2 can achieve, that the second receiver gets, would be generally be, it would be expected that this would be worse than what the first receiver would get. Right? Now this is one notion of degradation where we can clearly say it's physically degraded. Now let's look at another notion, okay, which will look pretty similar but is slightly different. So consider the following scenario where X is passed through an AWGN channel, Gaussian with zero mean and variance sigma 1 square. So he sees y1 at the output, and the second receiver gets y2. So this is passed through an AWGN channel with zero mean and variance sigma 1 square plus sigma 2 square. Okay. So in some sense, if you look at, well, user 1 is essentially getting y1 which is identically distributed with respect to this, right? So these two are essentially the same. But what y2 sees, so once again, the channel from x to y2, if you just look at exclusively at the channel from x to y2, this is identical in distribution as the channel from this channel from x to y2, because here as well, so y2 is equal to x plus z1 plus z2, and z1 plus z2 is Gaussian with zero mean and variance sigma 1 square plus sigma 2 square. But here as well, in the second case, y2 is again obtained by passing x through an AWGN channel, where this Gaussian noise has variance sigma 1 square plus sigma 2 square. Right? So in some sense, even here, y2 is getting so y2 is in some sense degraded with respect to y1. But this scenario, note that is different from this particular scenario, because in this case, x, y1 and y2 clearly forms a Markov chain, whereas in this case, although the marginal distributions from x of y1 given x and y2 given x are the same as over here, the joint distribution of y1 y2 given x is different in this case than from this particular case. Right? So here x, y1, y2 do not form a Markov chain. Correct. So in this case, these do not form a Markov chain, but it's obvious that y2 is in some sense still degraded with respect to y1. Right. So this is an example where we say that y2 is stochastically degraded with respect to y1. All right. So I'll give again. I will recall the notion of degradation once again. But is this example completely clear, or are there any questions? Okay. So note that these two notions of degradation. So these two channels are obviously different, but in some sense intuitively it feels that y2 is degraded with respect to y1 in both cases. Here it's obvious that this is physically degraded, whereas here as well it's obvious that y2 is in some sense degraded with respect to y1, but it's different from this. So we say that y2 is stochastically degraded, or sometimes we just say that y2 is degraded with respect to y1 if the following happens. If you can represent the channel from x to y2 as a composition of two channels, one from y1 from x to y1 and from y1 to y2. Okay, and I note that this can be different than this. So all we're talking about is is how the marginal distributions are with respect to each other, but not the joint distribution, right? So this is a statement only with respect to the marginals and not with respect to the joint distribution, because even here uh, you can say that the channel from x to y2 can be written as a channel which is identical to the xy1 channel. So let me call this z1 prime and z2 prime. So the channel from x to y2 is a Gaussian channel with variance, with noise variance sigma 1 square plus sigma 2 square, and I can write this as a composition of two channels. Uh, one Gaussian channel with mean 0 and variance sigma 1 square, and another channel with variance with a Gaussian channel with mean 0 and variance sigma 2 square, right? Because any z which has variance sigma 1 square plus sigma 2 square can be written in some sense as a sum of two independent Gaussians, one with variance sigma 1 square and one with variance sigma 2 square. So this is y2. Right? So this particular channel is being represented in this particular fashion. So I can call this maybe y1 prime. So note that uh, the the distribution of y1 prime given x is the same as the distribution of y1 given x. Although the distributions are the same, these y1 prime and y1 are independent of each other, right? And that's important to note. So that is the difference between stochastic degradation and physical degradation. In physical degradation, y2 is indeed obtained by passing y1 through another channel, physically passing y1 through another channel. But in stochastic degradation, the effect that you get of y1 is the same effect as though you're passing y1 or maybe an independent but identically distributed copy of y1 through uh, through another channel. So physical. So if y2 is physically degraded with respect to y1, then y2 is obtained passing y1 through some channel py2 given y1. But in the case of stochastic degradation, y2, I should be a little more careful when I say this. So y2 could be obtained. So if a channel is physically degraded, then it is also stochastically, sorry, if a channel is stochastically degraded, uh, my bad. If a channel is physically degraded with respect to y1, if y2 is physically degraded with respect to y1, then it is also stochastically degraded with respect to y1. But so physical degradation implies stochastic degradation, but in general, stochastic degradation does not imply physical degradation. So y2 is obtained by passing maybe y1 prime, which is identically distributed with respect to y1. So y1 prime could be independent of y1, or it could be y1 itself, because if it is physically degraded, then it's then y2 is obtained by passing y1 through p y2 given y1. But it could also be the following case over here, where you are passing an independent but identically distributed copy through py2 given y1. All right. So that's the difference between physical and stochastic degradation. So in general, it's degraded if the following holds: if you can represent the channel or the PMF py2 given x as a composition of two PMFs, py2 given y1 and y1 given x. All right. And this implies, so degradation implies that so this obviously implies that the mutual information between x1 and y is going to be greater than or equal to the mutual information between x2 and y, and this holds for all put x and y1 versus x and y2, x and y2, and this holds for all input distributions px. Right, so this obviously means that the capacity of the first channel is going to be greater than or equal to the capacity for the second channel. But note that this condition does not imply degradedness. Right, so this direction holds, but this direction does not necessarily hold. And in fact, for such channels, so you can consider a channel of which satisfies this property, that the mutual information between x and y1 is greater than or equal to the mutual information between x and y2 for all possible input distributions. This is another class of channels which may or may not be degraded, may or may not be a class of degraded channels. But for this class of channels, we'll see that we can exactly characterize the capacity region, whereas for these channels, we still don't know how to characterize the capacity region. All right, and so to just show that this condition does not imply degradedness, we look at one particular example, and this is something that was there in your first assignment. That is a BEC versus a BSC. Okay, so the question is a BEC, let's take 0.4, degraded with respect to a BSC, maybe take something small, 0.01. All right, so this is the question: is a BEC 0.4 degraded with respect to a BSC 0.01? So clearly, the capacity of this is much smaller than the capacity of this particular channel. The capacity of a BEC 0.4 is 1 minus P, 1 minus 0.4, which is 0.6. Whereas the capacity of this channel, the BSC 0.01, is 1 minus the binary entropy of 0.01, which would be something close to 0.9 something. Right, so this is an obvious channel where in some sense this channel is worse than this channel, but this channel is not degraded with respect to this particular channel. All right. And the reason is because the BECP cannot be written as a BSC 0.01 passed through some other channel. So if this were to be degraded, then we should be able to write the BEC 0.4 as though you are passing X through a BSC 0.01 and then passing this through some other channel. Let's call it channel 2 to get Y. So if these two are identically distributed, then if we can find such a channel for which this has the same distribution as this, then we would say that the BEC 0.4 is degraded with respect to the BSC 0.01, but this is not the case. This is not degraded. Right? And a simple reason why this is true is the following. So if you look at a BEC 0.4, right? So this is what the channel looks like. The inputs are either 0 or 1. The outputs are either 0, 1 or an erasure. So the probability Py given X of 0 given 0. So this is whatever 0.4. All right, so this is 0.6. And similarly, the probability of seeing a 1 given 1 is also 0.6. Right? So here, one way to think about this is that now if you see, if you consider a BEC, right? At the output, if you see a 0, then you know for sure that a 0 was transmitted at the input. All right? Just by looking at this, you can see. So the probability that X equal to 0, given that Y equal to 0, is 1. But if you pass X through a BSC and then through some other channel, maybe you pass X through a BSC 0.01, right? And then maybe pass this through some other channel. Potentially there are connections between this and this, 0, 1 and erasure. Then clearly if you see, if you look at the concatenation of these two, you can get a Y equal to 0 if you see that Y equal to 0, then X could have been 0 or it could have been 1. Right? You don't know for sure. You can never say with probability 1 whether the actual transmitted X was 0 or the actual transmitted X was equal to 1, because you're already corrupting 1. So a bit could have been flipped with a small probability, but it's still a non-zero probability. All right, and that is really the reason why you cannot obtain a BEC as a composition of a BSC with any other channel. Okay, so in this particular case, 0 and 1 will always be confused, whereas in this case, 0 and 1 can never be confused. Right? So in particular, so Py given X of 0 given 1 and Py given X of 1 given 0, these are equal to 0, exactly equal to 0. Whereas if you look at the composition of this with any other channel, the probability X, let me call it P tilde as the composition of these two, P tilde Y given X of 0 given 1 is strictly greater than 0, right? Because you can get a 0 if I mean, so there has to be either you get 0 from 0 or 0 from 1. But both of these you can get it from 1. So there is a transition from 1 to 0, and there is a transition from 0 to 1. So no matter how you arrive at 0 over here, it has to come either like this or like this or like this. So there are connections everywhere, both from 0 and from 1. So, so if you took the composition, then the probability, then given that you've seen a 0 at the output, it is still possible that a 1 could have been transmitted at the input. Right? And that is why a BEC 0.4 is not degraded with respect to a BSC 0.01. All right. In any questions? All right. Yeah. So that is why there are different notions of one channel being stronger than the other. So clearly, in this case, the BEC point zero, the BSC 0.01 is in some sense stronger or better than the BEC 0.4, but that does not mean that it is that one is degraded with respect to the other. Right? Because if you take channels in terms of capacity, then no matter which two channels you give, you can always say that okay, the capacity of one is greater than the other, or equal to the other, or less than the other. Right? So you can always say that okay, this channel is better than the other in terms of capacity. Whereas uh, you can't say that one channel is always degraded with respect to the other. So in this case, this channel is not degraded with respect to this, and of course, obviously, this channel is not degraded with respect to this particular channel. So there are different notions uh, of one channel being better than the other. Okay, and that's an important notion to keep in mind. And so our discussion uh, on broadcast channels will be primarily with respect to degraded broadcast channels, because in this case we can say what the exact capacity region is. And in fact, the capacity can be, we'll show that that capacity can be achieved using a rather simple scheme, one which is called superposition coding and successive interference cancellation decoding. Okay, and all right. So to start with, to understand the ideas behind superposition coding, we'll look at a simple broadcast channel. So it's the binary symmetric broadcast channel, which I had introduced in the previous class. And the channel is the following. You take at each time instant I, x of I is passed through a BSC P1 to get the first receiver's output, y1 of I, and it's passed through an independent BSC P2 to get the second receiver's output. Right? And we'll, without loss of generality, we'll assume that uh, P1 is strictly less than P2, and P2 is strictly less than a half. So, so that is the channel that we're interested in, and for this channel we're interested to understand what is the capacity region. Okay, and in particular, can we do better than TDMA? Right? So if you look at TDMA, suppose we had to consider this. In fact, let's try to draw the achievable rate regions for this particular channel. Okay, so obviously this is So this is R1, this is R2, this point is C1, and this point is C2. So can someone tell me what are C1 and C2 for this particular channel? So for this particular binary symmetric broadcast channel, what are C1 and C2? What are the 2 points in the TDMA curve?
Sir, I of x y to y1 given y2.
It's not given y2, so it's just max of ix1.
Okay.
Because there's no given y2, right? So these channels are independent, right? So, but what will that be equal to? So this is general, right? This is any general broadcast channel. But for this particular channel, where you have for the binary symmetric broadcast channel, what are C1 and C2 equal to in terms of P1 and P2? Yes. So C1 is simply the capacity of the first channel, right? It is simply the capacity
Yes.
of
minus
this.
F1, sir.
Yes, so it's 1
1
minus
minus
h of P1.
2. Yes, sir. H1 P1.
So this is 1 minus h2 of P1, and this is 1 minus h2 of P2. Okay, fine. So we know that this region is achievable. Any region within this triangle is certainly achievable. But now the question is, can we do better? Right? And for this, we'll use what is called a superposition code. Now we can see that there's one channel. So user 1 sees a BSC P1, whereas user 2 is seeing a BSC P2, where P2 is greater than P1. So Y2 is getting, in some sense, more noise than Y1. So the second user is seeing more noise than Y1. Okay, and so if I can pack in more code words for like I should be able to pack in more code words for Y1 than for the second user for Y2. Okay, and so the coding scheme we'll use is the following. So first, let's assume that this is Hamming space, just geometrical description. So I'll consider a good channel code for the BSC P2. All right. Sorry, not the BSC P2. I'll consider one good channel code for user 2, so that user 2 can decode his message. Okay, so each message, so note that there are 2 messages, one intended for user 1 and another user for another message intended for user 2. So the messages of user 2 are going to be mapped to one of these green code words. Okay, in some sense, it's going to be identified with one of these green points in space. Okay, but actually what will be transmitted by the transmitter will be something slightly different. So for each green point, I'm going to identify, so each of these are what I call cloud centers. Okay, so corresponding to each of these, I'll consider some more code words which are essentially intended for user 1. Right. Okay, and so these blue points are what I call satellite code words. Okay, so these are called the cloud centers. The green points are the cloud centers, and the blue points are the satellite code words. So there will be 2 to the NR2 many cloud centers, one cloud center corresponding to each message for user 2, and I'll have 2 to the NR1 many satellite code words for each cloud center, right? So the total number of, so for each cloud center, I have 2 to the NR1 satellite code words. So the total number of satellite code words will be 2 to the NR1 times 2 to the NR2. So 2 to the N times R1 plus R2. All right. So this is sort of the code. Okay. So suppose that I get one particular message. So I want to encode a message M1 comma M2. Okay. What does the encoder do? The encoder first sees M2. So corresponding to the message for user 2, corresponding to M2, there will be one cloud center associated with it. Okay. So corresponding to M2, maybe this is the cloud center associated with M2. Okay, and corresponding to M1. So now you see what M1 is, and for that M1 you identify the corresponding satellite code word. So this mapping between the M1 and the satellite code words and M2 and the cloud centers is done beforehand in some fashion. Okay, and that's part of the code book design. So you look at M2, M1, and find out which satellite code words corresponds to M1. Maybe it corresponds to this particular code word. So this code word will actually be transmitted through the channel. All right. So this code word is passed through the channel. So the user 1 will see a corrupted copy of this particular code word. So maybe user 1. So the noise to user 1 we'll assume is very, very small, whereas the noise to user 2 is much larger. So P2 is maybe much larger than P1. P1 is something which is very, very small. So user 1, so this is transmitted through the channel. The red point is what is transmitted through the channel. So user 1 will see something hopefully which is close to the red point. Right? So it's corrupted by a BSC P1 where P1 is very small. Maybe this is what user 1 sees. It's corrupted slightly. Whereas now user 2 sees this corrupted by a BSC P2. So P2 could in general be much larger than P1. So maybe user 2 sees something which is farther away. So this is what user 2 gets, whereas user 1 sees this blue point. Okay. Now what does user 1 want to do? User 1 wants to identify its message M1. Correct, but hopefully if the code book is designed well enough, then user 2 should be able to find the closest code word in this entire code book. So it looks at all possible satellite code words, finds the closest satellite code word to it. So it could be in this cluster or in this cluster or in this cluster. It could be in any cluster. All right, but it first tries to identify the closest code word, And maybe so in this case it's obvious that this is the closest code word. The red point is indeed the closest code word. Okay. Now user 2, obviously the user 2 sees a worse channel, so there's a lot of corruption. So user 2 obviously cannot decode to any of the blue points because the blue points are all very tightly clustered to each other. But user 2 doesn't really have to identify which of the blue points was transmitted. All user 2 wants is the message, and this corresponds to one of the cloud centers. So user 2 will try to find the closest cloud center and not the actual closest code word. So the blue points are the actual code words, whereas the green points are all the cloud centers. Right? So user 1 will try to decode to the closest code word, which is the closest satellite code word, whereas user 2 will not decode to the closest satellite code word. It will try to find what is the nearest cloud center. And in this case, hopefully, if the number of corruptions is not too large, this will be decoded as this green satellite code word, which actually corresponds to M2. Obviously, if the corruptions are too much, with some probability this could go wrong, and maybe user 2 would decode to this cloud center or maybe this cloud center, depending on how far the noise has taken it. And the same could happen to user 1 as well. If with some probability it would decode to one of the other satellite code words in that particular cloud center, or a satellite code word in some other corresponding to some other cloud. All right. So that's the sort of the basic idea behind superposition coding. You instead of unlike coding for the point-to-point channel, where all code words would be either all of them would be clustered in one particular region, or they would be kind of uniformly distributed. For the BSC, we considered a code where code words were kind of equally spaced apart. That would be sort of the best case for the point-to-point BSC. But for a broadcast channel, for the binary symmetric broadcast channel, the sort of optimal code looks something like this. So it's a superposition code where code words are sort of in different clusters. Each cluster corresponds to cluster corresponds to one cloud center and corresponds to one message for the second user. And within each cluster, you have different code words, and hopefully the user 1 is going to be able to uniquely identify which code word was transmitted. But since the second user is not as capable as the first user, since the second user is degraded with respect to the first user, it can't really identify what the exact code word was, but then it should be able to at least decode to the closest cloud center. All right. So any questions regarding this intuition? This is just high-level intuition. We'll make this a little more formal soon. So this is sort of the geometric description of what is to come, and we'll prove exactly what rates are achievable and so on for this case. Okay, so let me just give a quick sneak peek as to what rates are achievable in this case. So one way of viewing a satellite code word is as though you pass the cloud center through some particular channel. In fact, a BSC alpha. So it's as though, I mean, this is just heuristic interpretation. So let's assume that the satellite code word, so we'll assume that, so you identify these cloud centers which are going to be uniformly distributed, so uniformly spaced apart. But from each cloud center, the satellite code words will all be within a certain distance of the corresponding cloud center. In fact, let's take that the total distance is going to be at most n times alpha. Okay, so you fix some parameter alpha and choose code words within a distance of n alpha to the corresponding cloud center. Now, user 1 should be able to both identify the correct cloud center as well as the satellite code word within the cloud center. All right. So it turns out that the R1 that you can achieve should satisfy the following condition. So since it's as though you're passing these satellite code words through a BSC P1, and in addition to that, each code word is constrained because it has to lie within a ball of radius alpha n times alpha of the cloud center. So as long as R1 is less than or equal to H2 of alpha star P1 minus H2 of P1, user 1 is going to be able to decode the message correctly, its own message correctly. Right, so this corresponds to sort of a constraint on sort of the radius of the cluster. Each cluster or each cloud, if you like to call it. All right, and now the second user only has to decode the correct cloud center, but unfortunately, there are two forces at play. One is the BSC-P2 itself, and another force is that you're not transmitting the cloud center itself. You're transmitting one of the satellite code words, which are going to be within a certain distance of the cloud center. Right, so the view for user 2 is as though you transmitted the cloud center through a BSC. So in some sense, so this is the message for user 2, or the cloud center was passed through a BSC alpha to get the satellite code word, and then through a BSC P2 in order to get Y2. Okay. Again, this is heuristic interpretation. This is not exactly what is done, because after all, what is transmitted is a satellite code word. So this is the actual xn. We call this x tilde 2. Okay, so this is essentially as though you're passing the cloud center through this composition of two BSCs, which is essentially a BSC alpha star P2. So any rate below the capacity of this channel is achievable for user 2, and that is 1 minus H2 of alpha star P2. So recall that alpha star P2 is equal to alpha into 1 minus P2 plus 1 minus alpha times P2. Correct? So now alpha is a free parameter. It's the radius of the cluster, which you can vary as you want, and certainly any rate pair satisfying these two inequalities is achievable. Okay? And as you vary alpha, you get some particular rate region, and that rate region is what is, so it gives you some set of rate pairs at which you can certainly operate. So you can drive the probability of error down to 0. So PE can be made to go down to 0 as long as these two conditions are satisfied. So the next class we'll see what this rate region looks like, And then so this was again some heuristic, but we'll see what exactly this gives us for the binary symmetric broadcast channel, and we'll see the exact mechanism of encoding and decoding for a general broadcast channel. So for any general broadcast channel, we'll get some set of rate pairs which are achievable. So it gives an inner bound, but this inner bound may or may not be tight for all channels. Okay, so we'll stop at this point and continue in the next class. Are there any questions? Any questions?
Sir, this is regarding homework 2, question number 2.2, sir.
Okay.
So means 2.1 and second question that we have that A is random M cross N matrix.
Okay, just
That
give me 1 second. I'll try to pull it up. Okay, so homework 2. Exercise 2.2, is it?
no, 2.1 question number
2.1.
2.
Okay.
Question number second question, sir.
Okay.
So entry of A element of A matrix AI of J with Bernoulli half. So
Correct.
what would be the element, like any real number or 0 or 1?
No, it's always 0 or 1. It's
Zero.
IID Bernoulli
Yes.
half, right? So it's 0
Yes.
or 1.
Okay, sir.
So it's 0 or 1. The probability that Aij is equal to 0 is half. The probability that Aij equal to 1 is half.
Okay, sir.
All right. And you want to find the PMF of A times X.
Yes, sir. Yes.
Where of course the multiplication, so all the operations are modulo 2. Effectively, it's just XOR and
Yes, sir.
not the natural. Yes. Okay.
Okay, sir.
All right, good. Any other questions? Okay, so if there are no further questions, then we meet